spent the past few days solving quadratic equations. So now we're going to look at some scenarios where these might come up, some applications where we have to create a quadratic equation to solve it. This first example is one that we actually talked about in the last chapter. Let's see if it rings a bell. So you have a piece of machinery that is producing rectangular sheets of metal. And so let's go ahead and draw this rectangular sheet of metal where the length is 3 times the width. I don't know how wide it is, so I'm going to call that W, but the length then must be 3W. Now, let's see, equal size squares measuring 5 inches on each side can be cut from the corners. All right, so remember, we're going to cut out this corner and cut out this corner, and we know that these are 5-inch squares, so this is a big old piece of metal. Looks like this. And then what we're going to do is so these pieces are gone, these little squares are gone, and you're going to fold up all the tabs, and it's going to create this box that does not have a top on it, just an open box. You're going to fold it up. If the specifications call for the volume of the box to be 1,435 cubic inches, find the dimensions of the original piece of metal. All right, let's give it a shot. I know that the volume formula is length times width times height. Now, this is the volume of the box. So imagine all of these little tabs folded up. How long would the box be? Well, it would be this length right here, which used to be 3W, but I cut 5 out of each side. So now it's 3W minus 10. So there's your length, 3W minus 10. What do you think your width is? It is a W minus 10. And then once you fold up all those tabs, it's going to end up being 5 units tall. And I'm going to even erase, just save myself a step. I also know already that the volume is 1,435 cubic inches. Now, a couple ways you could do this. You could take the 5 and distribute it through one of the parentheses. You don't want to distribute it through both, because that's ultimately, then you're multiplying by 5 twice. But because I see that this left side is 1435, I'm just going to take both sides and divide it by 5. And that's going to divide very nicely. 1435 is going to be, let's see if I can do this in my head, 287. And then I'm going to go ahead and FOIL this next part together. (3W squared). Outer is a negative 30. Inner is a negative 10. So that's a negative 40W. Last, it's going to get you plus 100. And looky there, we have ourselves a quadratic. As promised, we're doing applications of quadratics. To solve this quadratic, I'm going to subtract the 287. So then I'm going to end up with 3W squared minus 40W. Subtract that 287, you're going to have a negative 187. Now, this is kind of some big numbers. I don't know what you'd prefer. Would you prefer to factor that or go quadratic formula? Neither way is ideal, but that's all right. I'm going to try factoring. So 3W and W, because I know that has to be the case. I have to have opposite signs, and I know that my outer and my inner are going to have to subtract to get me a 40 then, since the signs are opposite. All right, I just played around with some numbers. 187 doesn't seem like a very nice number, so I just divided it by some not so nice numbers, and I found that actually 187 is 17 times 11. And since those are both prime, I don't have any options but to use 17 and 11. Oops. You do want to pay attention to which one is getting multiplied. I think I actually want this to be an 11 and this to be a 17, because then I'm going to have a 33 and a 17. I lied. I'm going to swap those. Going back to this, because since they have to have a difference of 40, I need that to get bigger than 40. So 33 wasn't going to do it. So 3 times 17 is 51 minus 11. Yay, 40. Okay, I do want it to be a negative 40, so I'll put my negative there, positive there. Let's look at what we end up with solutions. I have W is going to be equal to 17 or to negative 11 thirds. Now, if we were just doing algebra, that would be just fine. But this is an actual application. Does it make any sense whatsoever to let your width here be a negative number? No way. Cross that guy out. So I know that my width is 17. Now let's make sure we answer the actual question. The question says, find the dimensions of the original piece of metal. That's this big rectangle. That was the original piece. And W is what I just found. So I found it to be 17. If I take 17 times 3, I get 51. And we are in inches. So I know the original dimensions. It was a 17 by 51 inch rectangle. Let's take a look at this type of a problem. This one is hinting at we're going to be using the Pythagorean theorem. So remember that from geometry, that works on right triangles. So we have a piece of property that's in the shape of a right triangle. So typically on these types of problems, I'm going to go ahead and draw a picture out to get a feel for what's happening here. All right, and then it says that the longer leg is 20 meters longer than twice the length of the short leg. Okay, that's kind of long-winded, but I'm going to back out of that and start with that short leg that it's referencing. I don't know how long the short leg is, so I'm just going to call it X. Now it says that the longer leg is 20 meters longer than twice the short leg. All right, well, twice the short leg would be 2x, but it's 20 meters longer than that. So that's going to be 2x plus 20. The hypotenuse is 10 meters longer than the long leg. Okay, well, if the long leg is 2x plus 20, then the hypotenuse is 2x plus 30. It says find the lengths of the sides of the triangular lot. Right, so I need to know what x is ultimately. And this is just a classic Pythagorean theorem. One leg squared plus the other leg squared is equal to the hypotenuse squared. Right, x squared plus square the first term, multiply the 2 and double it, square the last term, then we do it again, 4x squared, so 60x can turn into 120x plus 900. All righty. Obviously quadratic, we're going to need to get all the x's on one side here, it looks like. I would bring this 4x squared over, but it's going to cancel with that 4x squared. I'm just going to slash those two. They're going to cancel each other out. Now I'm going to bring the other stuff over. I'm going to have my x squared. I'm going to subtract the 120x. I'm going to subtract the 900. And this actually came out to some pretty darn nice numbers. In fact, so nice, I think that's very factorable. X and X. The factors of 500 that jump out at me are just 50 and 10, which is exactly what I want it to be. It's going to be a minus 50 and a plus 10. So it looks like X is either negative 10 or 50. And just like last time, you got to pay attention to, well, this really means something. It's not just algebra. It doesn't make any sense to have a leg be negative length. So I'm going to X out the negative 10, and that short leg is 50. So then your final answer should be written at answer the question. It wants the lengths of the sides of the lot. So I've got a 50, and what are our units? Meters. And then when I plug it into the other leg, it'd be 2 times 50 plus 20. So that's 120 meters. And then the last one would be 130 meters. These are the 3 side lengths. This problem is more of a graphing calculator kind of application. This is a formula that's actually used quite a bit, and you'll see it again in pre-calculus. It's vertical free fall motion. It's when something goes up and it just has this free fall coming back down. It looks like an upside down parabola. Something's going up and then it comes back down. All right, so you can see right here that yes, it's a quadratic and the A value is negative. All right, this right here is all the coefficient. This is like the A, this is your B, and this is your C of your quadratic. So this is measured. It says the height of an object in free fall is given by, and here's my function, and down here it tells you what all the variables mean. So T is your time, obviously. S is really measuring your height. I think of it like as position. S stands for the position, and in this situation, they mean the height of it. So it's the height with respect to the time. So it's going to go up, and then it's going to come back down. G is the acceleration due to gravity, which is 32 feet per square second on Earth. Now, if you're in physics, you maybe are more familiar with a 9.8 meters per square second, but here we will always use feet. If G is always going to be 32, ultimately you take half of that, that's 16, it's a negative 16. Sometimes you just see this formula written with the negative 16 here. So on your test, I'm going to give you this formula, but you have to know what to do with all the variables. So I will either give you a negative 16 or I will tell you that G is 32. You don't have to have that memorized. All right. The V is standing for your initial velocity. S, remember anytime this sub O right here, that is always initial. So initial velocity, initial height. So I'm giving you the formula. Let's just jump in and solve it. It says a pitching machine is rotated to throw pop-ups. It is set to throw with an initial velocity of 48 feet per second and from a height of 3.5 feet. Write the model. Okay, so the model means just write the function, filling in everything that you know. That's going to be S of t is equal to, we've already discussed it, negative 16 t squared. The initial velocity is 48 t plus the initial height is 3.5. That's the model. Now, once we have the model, it says what is the maximum height and the time that it takes to reach that height. So let's practice with our graphing calculator. This is a little bit tricky to do over a video, so have your calculator out. If you don't have it right now, pause the video and come back, and we're going to try graphing this. So they want it to find the maximum height. I know the maximum height is going to land right here on my parabola. So I'm going to look for that. I'm going to go into my y equals, and I'm going to type this function. So y equals negative 16x squared plus 48x plus 3.5. And before I even try to graph it, you might make sure that your plots are turned off. And then let's go to our window. And let's see what a reasonable window would be. The X is really this T. So you got to think about this. It's a pitching machine. It's a baseball, softball. It's going to go up and it's going to come back down. How long do you think that's in the air? Okay, it's not real long. I mean, if you think of a baseball game, the ball gets hit and boom. I mean, it gets caught or whatever pretty quickly. I'm going to go from 0 to, I don't know, I'm going to go 8 seconds. I think that's plenty. And I'm going to scale it by ones. Now the y is the height of the ball. So that you maybe don't know quite as well, but I know I'm going to start at 0, and maybe we go to, I don't know, let's go to 100 feet. Let's see what happens. Might be way too much. If it's way too much, then we'll adjust. I'm going to scale it by tens. Hit graph. All right, 100 was way too much, but it's fine. You should be looking at a nice little graph. And if you're using a graph to answer your questions, remember, I always like to see what it is you're looking at. So give me a quick scale. I went 1 to 8, or 0 to 8, and 0 to 100. And my graph looks like this. And I need this spot right here. Remember the go-to menu when you don't know where to go in your calculator? We go to second trace. If you go to that, you look down that, what do you think you're needing? Number 4, the maximum. And then if you read the little comment down at the bottom, it always kind of guides you through what to do. So it says, what's the left bound? It wants to know, it wants you to move your cursor left of the spot you're looking for. So you got to move your cursor so you're left of that peak there. So I don't know where your cursor is right now. You just got to move it. You can see the X and Y values. So I'm moving left, 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 and you press enter. And then it says, what's the right bound? So you're trying to like surround this peak. So I'm going to go right, right, right until I'm right of that peak. Press enter. Now, it asks you to make a guess. That's in case you have 2 peaks within your space, but I purposely only have 1, so I don't really care about the guess. So I'm just going to press enter, and it shoots back to me. Now, mine doesn't come out exactly. You have to understand that your calculator will not always give you the exact answer. Sometimes by the way it's calculating it, it gives you a bunch of decimals. So I have a 1.4999996, but it's really a 1.5. So this is a 1.5, and then my y value is 39.5. Now that's great, but that is not the answer I'm looking for. I am looking for a nice explanation of what is the maximum height and what is the time that it takes to reach that height. So you have to interpret what that means. So I would expect something like the max height. Remember, the height is the S or the Y value. So that is the 39.5 feet occurring at 1.5 seconds. All right, I might also ask you to find, when does the ball land on the ground? All right, that would be right here. And then you would go find the zeros. That's another option in that second trace menu. You could go find the 0 to see at what time it landed on the ground. So this is a pretty common little equation, and again, I would give this to you on the test. There's one more that I had the kids do on their own in class, but I'll just go ahead and go through it. Same kind of deal, a little bit different though. So this one says an object is launched vertically upward from the ground. Here's your initial velocity, neglecting air resistance, its height, S in feet, T seconds after the projection is, okay, all that verbiage to tell you right here is the formula. Notice I already put the -16 in there. The 100 is that initial velocity, but what's missing is my constant out here. Do you know why that constant is not there? That's my first question. Why is there not a constant there? Because it's 0. Remember, it said that it was launched vertically from the ground. It's starting at the ground. So if you were doing something like on my pitching machine, it was starting at 3.5 feet. It was up above. Maybe you are doing something where it's in the ground, then it might be a negative initial height. So it can be all those things. Now the next question says, after how many seconds will the object be 50 feet above the ground? Round to the nearest hundredth. Right, so I'm looking for when the height will be 50. So I'm going to put 50 in for the height. And I'm going to be solving for t. So I'm going to go ahead and get everything on the same side. I'm going to have 16t squared minus 100t plus 50. The fact that it says round to the nearest hundredth is probably my clue that it doesn't come out nice. This maybe doesn't factor. I could, I guess, pull a 2 out just to make my numbers smaller when I do try to do this problem. And then I'm going to use that factored version to run through quadratic formula. I don't know what this little equal sign is. It was 50 plus or minus that all over 2a, so all over 16. Okay, and I can actually do some of this in my head because I know 4 times 25 is 100, so that's 800. 2,500 minus 800 would be 1,700. So I end up with 50 plus or minus the square root of 1,700 all over 16. Now I'm just going to type that into my calculator. And in fact, I've already typed that into my calculator. And I got 2 answers. When I added, I got 5.70. And when I subtracted, I got 0.55. All right, so let's figure out what in the heck that means. Well, remember, you're solving for t. So these are times, and these are the times in which the object will be 50 feet above the ground. So why is it I'm getting 2 answers on that? Well, it's because my rocket or whatever that launched went up and it came back down. And right here is my 50 feet mark. It hit right here at 0.55 seconds and it hit right here at 5.7 seconds. So be sure you label this at for seconds, and you actually have 2 answers on that one. All right, the next question, as I promised earlier, how long before it takes for the object to return to the ground? So then I'm going to go ahead, and I hadn't really put this in my calculator yet, but I'm going to go ahead and do that now. Actually, you know what? I'm going to not, because I'm not going to mess with having to fix my new window and all of that stuff. I'm going to do this algebraically, because what I'm doing is, for it to hit the ground, then the height is 0. So let's just set it equal to 0 instead of equal to 50, which is pretty easy because now this is a pretty quick thing to try to solve. I'm going to pull out a GCF of, I guess, negative 4t would come out of that. And then I'd have 4t, and then it would be a minus 25. So that means t is 0, which I know that's the first time. That's when it started. The other one is going to be when it landed. So when I set that equal to 0, I get add 25 divide by 4. So I'd get 25 fourths, but it said to round to a decimal. Do you know what 25 fourths is as a decimal? All right, it would be 6.25. So this is, gosh, I totally ran out of room on this. Sorry, squeezing this in. So 6.25 seconds would be the answer to that one. Okay, lots of different types of problems on this homework. Go give it a shot. Have fun.